All right, welcome. We have made it to Wednesday. Wednesday 7 of the semester. We're pretty darn close to halfway through the semester. Maybe sometime next week is actual midterm. Speaking of next week, if you haven't looked at your syllabus lately, you might want to pull it out again. Exam 2 is next Friday. How did that happen so quickly? Nobody even knows. Well, I know. I planned it this way. I planned it this way because we're going to be ending probably, maybe even not today, probably, but by Friday, a unit, which is our fluids unit. And there's only really 2 homeworks on this unit, and it's a nice, convenient unit to have an exam after. So the exam next Friday will be only over chapter 14. It will only cover fluids, and it will only cover the homework that is due tomorrow and the one that is due next Thursday. Other than that, it will look very similar to the last exam. There'll be some problems. There'll be some concept questions maybe. It'll be a 50-minute in-class exam. Again, I will send out an email, but if you plan to take that exam remotely, I would like to know that sometime by the end of this week, so I can plan how I'm going to handle that. It's okay if you do, but I need to know that. I would like to know that ahead of time. I will try to get an equation sheet up for you by the end of this week. Are there any other questions? Or not other questions. Are there any questions, period? Okay, great. Then we can get back to it. So you might remember we left off Monday talking about this water clock problem. So I've discovered I honestly like doing my notes up here much less than doing them on the board. But one of the nice things is I can save this and bring it back the next time and not have to write a whole bunch of stuff more on the board. So this is actually where we were. We had written exactly this stuff on the virtual whiteboard. And we were thinking about how fast, really we want to know what the velocity of the water coming out of the bottom of this thing will be. And we had left off by writing the full Bernoulli's equation for 2 different points. For a point at the top of the water, of the cistern, of this tub, whatever it is that's holding our fluid, and then at the very bottom, right at the opening, you could imagine a little neck sticking down where this is. It doesn't really matter though. It could be a flat hole in the bottom of this. They will work exactly the same way. You just need to know the absolute distance between that point at which the opening exists and the top of the water cistern. The top of the water level at the top. So the only tricky part about this is straight up Bernoulli's equation. Bernoulli's for the top and Bernoulli for the bottom is realizing that, yes, there's atmospheric pressure on the top. The pressure at the bottom is also atmospheric at the point of the hole, because there is nothing now pushing up from above, and those 2 basically will cancel out. This could be done in vacuum, and it will work exactly the same as it's done at sea level. It can be done in a pressure chamber at high pressure. It doesn't matter because the pressure down is going to be exactly the same as the pressure up, and they will cancel each other out. Okay. So great. So you can put in P atmosphere for both of them and they actually cancel out. So what does this lead to? We can rewrite this. Oh, please take attendance. I'm going to close this up in a minute. If you are here, 2, 4, 6, 8, 2, 4, 6, 8. There's at least 5 of you who have not done this. Please do so if you're here. Again, this isn't for me. I don't really care, but the provost's office would like to know who was here on any given day. Okay, so those pressures go away. What we have is 1/2 rho velocity at the top squared plus rho g y at the top plus 1/2 rho velocity at the bottom squared plus rho g y at the bottom. And you'll notice there's a rho, it's a density in every single one of these terms. If we divide by density now, this is the density of the fluid, they all go away. So that's nice. It doesn't matter what the density of this fluid is, it will be the same. We're gonna get the same answer, no matter what the density is. So it's independent of the density of the fluid. So we can let's gather all the y terms on the left, let's gather all the v terms on the right. We get this. Yt minus yb times g, 1/2 the difference in the square of the velocities, vb squared minus vt squared. Oops. Let me get rid of this thing now. Okay, that's gonna be better. Okay, so we probably know, I mean, obviously you can be given anything in this problem, but in this problem we will probably be given the height of the water in the bucket or the cistern or whatever we're doing. And we're really gonna be wanting to solve for the velocity out the bottom. So let's call this h, the height of the tower. Okay, but these v's, we're going to need another equation for these v's. And for the v's, almost always when you're doing a problem like this, you're going to need to use the Bernoulli equation, and you're also going to have to use the other important equation that we've talked about with our non-static fluid section, and that's our mass continuity equation. We know that the surface area at the top times the velocity at the top must be equal to the surface area at the bottom, surface area, cross-sectional area, times the velocity at the bottom. Presumably, we would also have to be given the relative sizes of the opening at the top and the relative size of the opening at the bottom. That's going to be important for solving this problem. So we can plug this in. Let's solve this for VT and then plug VT in because we're going to want to solve for VT at the bottom, VB eventually. So VT is VB times AB over AT. So let's plug all that in. We've got GH on the left. We've got 1/2 VB squared minus AB over AT I don't have these squared in my notes, but they have to be squared. VT squared. That's right, right? Yeah. Okay. So, and this is VB, sorry. So they're both VB squared now. So we replaced VT with VB times AB over AT. We had to square that whole thing. They all get squared. We can pull the VB squared out now. And this is 1 minus AB squared over AT squared. Okay, so let's bring the 1/2 over. We got 2GH equals VB squared times, we can write this as, and you'll see why I'm going to do this in a minute, this is AT squared minus AB squared all over AT squared. Just changing the 1 to an AT squared over AT squared and combining those two terms. And then we're going to multiply, we're going to divide both sides by this term. VB squared equals 2GH times AT squared over AT squared minus AB squared. Now I can take the square root of both sides. VB squared, VB equals the square root of 2GH times the square root of AT squared over AT squared minus AB squared, all to the 1/2. Or if you like, the square root of 2GH times AT over the square root of AT squared minus AB squared. Those two are equivalent. Just squaring the numerator of that term and only square rooting the bottom of it. Okay, we've got a nice equation which relates the velocity out the bottom to our other known variables, meaning the height of the water in the cistern and the two areas, one and the other. Is this helpful? Where has this really gotten us? Well, we're going to assume, if we assume, and it's probably true, that the hole in the bottom of our cistern is much, much smaller than the top of our cistern, then we can make some simplifying assumptions here. If AT is much, much bigger than AB, which it most likely is, it's not a very good water clock if it's just going to all fall out the bottom instantaneously. You probably have a pretty small opening if you're going to use this in any sort of real way. Then what happens to this term? AT squared minus AB squared is about what? It's about the same as AT squared. AT is already much, much bigger than AB. Adding the two isn't going to be much different than AT. Squaring them both and then adding them is going to be even worse. This is basically AT squared. And if that's true, then the square root of AT squared minus AB squared is basically just AT, and those two just cancel out. This whole term, AT over the square root of AT squared minus AB squared, is basically 1. It basically goes away. And that means that our velocity out the bottom is roughly square root of 2GH. And that, assuming that we're not draining our thing too fast, that H isn't changing all that much in a short amount of time, is a constant. And so you can, if you like, use this as a water clock, because the velocity of the water out the bottom will be at a roughly constant rate, as long as you're not draining this thing too fast. And then you can set your clock to measure a certain volume of water per hour or per second or per hour, or a certain mass of water per second or per hour, and design your water clock appropriately. By the way, this is a result that's just going to come up a lot. V equals square root of 2GH. You're gonna be doing these problems, and it's not going to seem like a water clock problem, and you're going to get to the end, and the answer is going to be root 2GH, and you'll be like, oh yeah, I guess this is a water clock problem. It makes sense now. That's what I'm saying. I know. It only depends because, well, there's two competing factors that cancel each other. The bigger the density of the water, the more mass there is. But the bigger the density of the water, the more pressure there is at just above the at depths that are equivalent to the hole, not right at the hole. Think about that. So they kind of, I had a profound thought there, and it's not really making much sense to me now that I'm saying it out loud, which is sad. But yes, The answer is it doesn't matter. Think about why this actually is. The density doesn't matter. You could have mercury in there, you could have oil in there. It will come out at the same rate. Okay, here's a cool challenge problem for you. If you are interested in challenge problems and like to think hard about this, question, Isaac. Of course, of course, of course. All of our assumptions that we made at the beginning of this fluid's in motion, there's no eddies, there's incompressible fluid, there is no viscous. Obviously, if you have a very viscous fluid, it's going to drop much more slowly out of that thing. We're assuming non-viscous fluid. That's right. Exactly. And for the most part, for water, there's not going to, unless you make that hole really, really small, it's going to be a pretty small change. But if you put honey in that thing, or if you put in pine tar or something that has really, really high viscosity, obviously that's going to change everything. Yeah, that's right. Other questions about this? Okay, what is a challenge problem? If you like working on challenge problems, here's your challenge problem for the day. It is possible to design a water clock here we go. Whose shape is such that, now we've just been talking about a cistern where you have, I don't know, it could be a circular shape, but the sides are flat. It's possible to design the shape of a container that holds your liquid such that you don't have to, such that the area changes as a function of height, right? It might get bigger or it might get smaller as a function of height, such that at all times, without making any approximations, the velocity through the bottom will be constant. Your challenge problem is, without even making the assumption that AT is much, much bigger than AB, what shape of container exists, is there? What would the shape of a container be such that the velocity out the bottom is a constant at all times? With no approximations. What would the shape, what would that container look like? So A is a function of T. A is a function of height, of Y, as you go up. That's right. The area has to be getting smaller as you move down, but it's not a linear function. So yeah, you're right. The general shape is that, but what is the exact shape? What will this thing actually look like? What? A what form? Solve the problem, and you'll see. A hemisphere. Okay. These are good guesses. An hourglass, a hemisphere, a cone. None of them are exactly right. You have to solve the equation to get the true form of the shape, and it's kind of interesting. We can talk if you're yeah, we'll talk Friday. Bring your solutions Friday, and we'll really what I want. So area is a function of height, yes, but really let's think about this with the circular cross section. What would the radius be of this thing as a function of height? Right? So what is that actually going to look like? So bring your solutions Friday. We'll discuss them. Okay, let's do another example. Household plumbing. Okay, so here is the basic idea. There is a pipe underground that brings water to your house. This pipe has a certain pressure in it. This is exactly how the municipal water system works, by the way. They exert some positive pressure on the water that they're forcing down pipes, and then you connect to that pipe and bring the water up into your house, where you might want to turn a faucet on and have that water come out. So this is the general picture that we're talking about. Let's talk about the area. We'll talk about two sections of the pipe. Again, we're talking about the area of pipe 1 and the area of pipe 2. They'll have different cross-sectional areas maybe. We will have at different heights, right? The height of your sink or your faucet, wherever you're trying to get it out of your house, and compared to the height of the pipe in your basement. So that's the picture. Here are the words. Pipe carries water into basement of house. And that pipe has diameter, we'll call it D1, with D1 equals 2.5 centimeters. The gauge pressure and this is supplied by your municipal water company, is 170 kilopascals, and we'll call that PG. Now, this is the gauge pressure, right? So this is really the true pressure in here plus atmospheric, because atmospheric is going to be outside. So the true pressure, if you wanted to actually put the pressure here, would be this plus another 100 kilopascals, but it's more like 270 kilopascals. This is the difference between the pressure of the water inside the pipe and atmospheric. That's what gauge pressure is. Okay, another pipe carries the water up to a second floor sink. Has anybody ever seen the movie The Jerk, Steve Martin movie comedy? It's a funny movie. There's a great scene in there where he's this country bumpkin, doesn't know anything, gets into this rich fancy house, and he turns on the water faucet and water just comes out of it. It's like, whoa, how did they get the water all the way up to the second floor? Well, the answer is water pressure. And its diameter, let's call this D2, equals 1.2 centimeters, about half the size. And let's say that delta Y is 8 meters. It's 8 meters from the basement pipe where it comes in to the second floor sink where the water is going to be coming out. So we're going to solve this problem twice. The first time, we're not going to let any water flow through. The question is, how much force do we need to exert on a plate that we're holding over the pipe to keep the water from coming out? Say, to close the faucet, a disc is held by a valve to stop the flow. The question first is, with no water flowing, what force is needed to hold it there? Okay, let's write down Bernoulli's equation. This is a statics problem. I don't necessarily need it, but well, it's instructive to do so. So let's go ahead and do this. P1 plus 1/2 rho V1 squared equals rho plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho V2 plus, rho G Y2. In the statics case, the velocities are all 0. They go away. So we're left with this equation. P1 plus rho GY1 equals P2 plus rho GY2. Let's solve this for P2. The pressure at the top is equal to the pressure at the bottom plus rho times G times Y1 minus Y2. Does this look familiar? This should look familiar to you. This is an equation straight out of the statics part of this section, which is good. In the absence of motion, this Bernoulli equation reduces to the equation that we had before. Delta P equals rho G delta Y. This has to be equal to, if we weren't solving for the force that we need on the plate, the pressure at point 2 is exactly what we need. How much force do we need? Well, that's going to be the pressure times the area. So the pressure is going to be the force divided by the force that we need to hold that plate in there, divided by the area of the plate, area of the pipe. And this is specifically got to be A2. Okay. Now, this is where it can get a little tricky. Force over area, we know, is P1. What is Y1 in this case? This is where you have to worry about signs. Remember I said H and delta Y and Y's have different signs? This is one of those cases where you have to worry about the signs of delta Y, because whether you're adding or subtracting makes a big difference here. So what is Y1 in this case? We don't know. We can set our 0 point anywhere. Let's set our 0 point to be Y1 at the basement. If Y1 is 0, then what is Y2? If delta Y is 8 meters. It's 8 meters, right? So Y always counts up. That's the difference between Y and H. Y counts up, H counts down. So Y is positive 8 meters. If we had set Y2 to be 0, then Y1 would be negative 8 meters. It doesn't matter what we choose as our 0 point, but we know that Y2 has to be bigger than Y1 because it's physically up against the force of gravity. That means that this is really minus rho G delta Y from above, where delta Y is 8 meters. We can't just plug in a positive 8 meters there. We have to know what the orientation physically is. Delta Y really is negative 8 meters in this particular case, the way we defined Y1 minus Y2. Or, if you like, Y1 minus Y2 is the negative of delta Y, which is 8 meters. You're looking confused. Okay. Be careful with these signs. It's very easy to get that sign wrong. Just plug in 8 meters and be done with it. Yes. That's right. That's right. It's going to be non-physical and nonsensical if you plug it in the wrong way. And so thinking about this in terms of how the numbers look is also a valid way to do it. That's right. But if you get to this problem and you get it all wrong, and you have no idea why, and you haven't been thinking about these things as you go along, make sure you go back and make sure you've got your delta Y in the right sign, in the right direction. Okay, great. So we know that P1 is the gauge pressure. So what is P1? Is the gauge pressure plus the atmospheric pressure, right? Because we know that the pipe has gauge pressure plus also atmospheric pressure. We can ignore, and you often can ignore the atmospheric pressure because, yes, there's an extra atmospheric pressure pushing on the pipe water, but there's also atmospheric pressure pushing down on our plate from above. And those things will cancel out. And so again, we could perform this experiment in a vacuum. We could perform this experiment in some high pressure chamber. It will work exactly the same because those two things are being pointed in both directions. We can ignore it. So the total force is going to be independent of that atmospheric pressure. But P atmosphere also pushes down from above. And so you can ignore it. So we get F over A 2 equals the gauge pressure minus rho G delta Y. And now we have, we can solve this for the force. We've got pi, bring the A over, and it's, we know it's pi times the radius squared, or pi over the diameter over 2 quantity squared times the gauge pressure minus rho G delta Y. Plug in some numbers. I'll just write them out. Pi times 0.6 centimeters, quantity squared, times 170 kPa, minus 1,000, this is water, it's 1,000 kilograms per cubic meter, times 9.8 meters per second, times meters per second squared, times 8 meters, and you get a number that is about 10.4 newtons. Which ain't too bad. So you could put a plate on top of this pipe and put a little bit more than 1 kilogram weight on it, and it would be able to hold it there, and you would have no water coming up. Any less than that, and the water pressure is going to win, and there's water going to be spewing out of your faucet. Okay, now, that was interesting, but that was a statics problem. Let's turn the faucet on and see what happens. Now, we get the full Bernoulli in all of its glory. So the question we're really wanting to ask is, how fast will the water be coming out of this faucet when we turn the water on? We're really looking for V2. Okay. Okay. So let's write down Bernoulli again. P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. Okay, we know that P1, the pressure down there, is the gauge pressure plus atmospheric pressure. What's P2? Again, we're thinking about the pressure after we have released the plate and are allowing the water to flow freely. It doesn't matter if it's flowing straight up or out the side or straight down. That makes no difference. What is the atmosphere? What is the pressure? Sorry, what is the pressure of the fluid as it's coming out of that opening? It's atmospheric, right? Anytime you have water freely flowing through space, not confined to anything, particular thing, in free fall, which is the case as soon as it enters, as soon as it comes out of the faucet, that is only experiencing an atmospheric pressure. That's the only pressure acting on it. Is just P atmosphere. Okay, so let's bring the things that we know. Let's write it. Let's actually plug these in. So P1, we have PG plus P atmosphere plus 1/2 rho V1 plus rho GY1 equals P atmosphere plus 1/2 rho V2 squared plus rho GY2. Okay, P atmosphere, let's subtract it from both sides of our equation. It's on there both times. We can, and now again, doesn't matter if we're conducting this experiment in a vacuum chamber or not. Goes away. Let's bring all the things that we know to the left-hand side of this equation and all the things that we don't know to the right-hand side of this equation. So we know what the gauge pressure is, but we don't know what the velocity is, but we do know what the y's are. So I've got PG, and that should be a subscript G, the gauge pressure, plus rho G times Y1 minus Y2. I've done a little bit of basically the same thing I did before. I'm bringing the Y2 term over, and I'm subtracting the two and combining terms. Equals, the terms I don't know are the ones with the velocity. So let's move all those to the right-hand side of the equation. 1/2 rho V2 squared minus V1 squared. With me? Okay. What is Y1 minus Y2? That is our negative delta Y from before. We can do the same thing we did before. Let's call that negative delta Y. So now we can plug in negative delta Y. This becomes PG minus rho G delta Y equals 1/2 rho V2 squared minus V1 squared. Okay, now we need to know, we want to know what the V's are. We've got one equation and two unknowns. We're going to need another equation to figure out what these V's are. Which equation should we use? Go ahead, Isaac. Exactly. The mass continuity equation. We know what the relative areas of these two pipes are. That should give us the relative velocities in these two pipes, and that should be our second equation that has the two V's plus the things that we know, the areas of the pipes, and that should be enough to get this done. We know that A1V1 equals A2V2. And now we've got two equations and two unknowns. We can solve for both of them. So let's plug in, let's sorry? We are. Yeah, and for some reason in my notes, I solve for V2 and then plug V2 in and then solve for V1. So I'm gonna do that, even though it's probably easier to do this solving for V2. So, so do I want to do this the smart way or do I want to do it the way it's in my notes? Yeah, I know. Because then you can plug V1 in and just solve for V2 and be done with it. Yeah, I did it the opposite way in my notes for some reason. All right, let's do it the smart way. And I'll try to, you have to help me because my notes now, I don't have anything to help me out here. Okay, so V1 equals V2 times A2 over A1. We can plug that in. And we get PG minus rho G delta Y equals 1/2 rho times V2 squared minus V1 squared, which is V2 squared times A2 squared over A1 squared. Oh, look, we've got a ratio of areas squared again. We've seen that one before, haven't we? This comes up a lot. There's only so many ways. This equation always sort of leads itself down the same path. Okay, that is 1/2 rho. Let's pull out the V2 squared times 1 minus A2 squared minus A1 squared. And that, again, we're gonna need to be dividing by this. So it's better to have instead of a negative sign, an actual, well, it's better to split this up. This is 1/2 rho V2 squared. Let's make this A1 squared over A1 squared, and then distribute terms, A1 squared minus E2 squared over A1 squared. Yeah? Okay, let's solve for V2. V2, I'm gonna have to do this out. I would just skip to the end here, but my notes are wrong now. So V2 squared has to be 2 gauge pressure minus rho G delta Y divided by rho times A1 squared over A1 squared minus A2 squared. Is everybody happy with that? Excellent. Now you just take the square root of both sides. So V, you can write it again in your notes if you want. I'm just going to erase this and put a square root here. That's our number. And these are all things on the right now that we know. We know the gauge pressure, we know the density, we know G, we know delta Y, and we know both of the A's. You can plug a number in. I didn't solve this for V1, for V2. I can tell you that if you solve this for V2 and then plug back in to find V1, you should find that V1 is 3.2 meters per second or so. And this, R1, is V1 times A1 is 1450 centimeters cubed per second, cubic centimeters per second, which is about 1.5 liters per second. And that will be the same in pipe 1 and pipe 2. So this is probably way faster than you would want your water to be coming out of your pipe. This is a gallon every 3 seconds or so. So, you know, usually there's some other things that are keeping your water from coming out of your pipe that fast, or you have a smaller nozzle or something. Actually, that wouldn't help you. Some other thing to stop the pressure from letting the water out so fast. Anyway, that's it. That's pretty much the most complex question we could think about. There are certainly more complex problems to think about, and you'll be dealing with some more complex problems on the homework assignment, but the concepts are no different than what we've been talking about here. Okay, let's see how much you have learned about Bernoulli's equations. Let's do some concept questions. So let's see how we are. Well, let's just go to the concept questions. These are an excellent way to test how much you've learned. So we've got the following pipe system. We have a small pipe at a certain height that gets bigger, and then takes a U-turn and goes down at the same diameter, and then gets bigger again. Okay, thusly. The question is, where is the velocity the highest? Pull out your top hat answering devices. Where is the velocity highest? I've got 4 points there, point 1, 2, 3, and 4 in the diagram. In which of them is the velocity the highest? 1, 2, 3, or 4, or A for 1, B for 2, C for 3, D for 4, or E, are they all the same? So let's see what we've got. Where is the velocity highest? Question mark. You've got 5 choices, and go. And I don't have any, I hope nobody wants to text this answer in because I'm getting no information about. Is anybody using SMS to answer these questions? Okay, then I won't worry about it. "30 seconds left. Which pipe section has the highest velocity?" "20 seconds left. It's hard to scratch your chin with a mask. Doesn't work as well. 10 seconds left. Again, the points don't matter, and the questions are real though. So useful to know where you stand. Oh, now they tell me the text number. This has gotten kind of weird. All right, let's take a look at the results. Hey, okay, great. 28 of the 31 people who answered put in A, pipe section 1. Let's hope that's right. Anybody want to make an argument for why it has to be section 1? Go ahead, Bailey. Yes. That's exactly right. This is a pure conservation of mass velocity problem. The R's have to be the same. This is a closed system. The total volume flow rate and mass flow rate have to be the same through all sections of this pipe. Since the diameter, the area of pipe 1 is substantially smaller, R is just V times A. If A is very small, then V must be much larger to correspond. That's right. It will be the fluid will be moving fastest in the reach of the pipe that is the smallest in a closed system where things are moving through. Okay, here's a harder one. The question was, for the people at Zoom who might not have been able to hear it, what if delta Y, this section was really, really big? Could it be that this is big enough that you would get slightly higher velocity, say here, than here, irrespective of the pipe differences? Is that what you're saying, basically? Right, but let's take that out. I'm saying that 2 and 3 should be the same, and you're saying if delta Y is high enough, is it possible to get 3 higher than 2? Is that what you're saying? No. If our fluid is incompressible, if our fluid is compressible, then you have the game changes. If the fluid is incompressible, and this is a truly closed system, you cannot move faster here than you're moving here, simply because, again, you'd be developing vacuum. You'd be losing fluid there somehow. You'd have to have an exit gate for that fluid to get somewhere. That's right. That's exactly right. You had the right concept there. So it might seem like it should be moving faster in 3 than 2, but if it's a closed system and this fluid is incompressible, that is not the case. It cannot be moving any faster in 2 than it is in 3, or vice versa. Yeah, that's exactly right. That's right. It's a higher pressure, but the potential energy is different. That's right. Those two things completely offset each other. That's what the velocities are the same. That's exactly right. Pressure is kind of like a counteracting potential energy term. That's right. Okay, now this actually is probably a simpler one. Where is the flow rate the highest? 1, 2, 3, or 4? You got 5 choices. I'm only gonna give you 30 seconds for this one because this one should be really easy. 1, 2, 3, 4, or all the same. 20 seconds left. I did say it. It's true. And if you got one right, you assumed it to get it right. But hopefully everybody will get this one right. 6 seconds left. Okay, I'm going to stop it there. What do we got on time? Oh, I'm over time. Crap. Oh, okay. Well, more people got this one wrong than the last one. It has to be all the same. The flow rate, meaning the volume, the velocity times the area, has to be the same in all sections of this pipe. I don't have time to ask this question, sadly, but the next 2 questions I'm going to ask are: where is the pressure highest? Oh, where the pressure is highest? So you can bank that question, and we'll ask it at the beginning of class on Friday.